I'm adding this podcast here at the end of chapter 6 from a paper that just came out in the proceedings of the National Academies of Science. And I'm adding this here because I think it's very relevant for an introduction to climate science, climate change, climate solutions, and so on. More related to the climate science and global warming. We have already seen global warming in terms of how the surface temperatures are warming. We've talked about the science of its impacts, etc. But we also talked about how warmer temperatures hold more moisture. So does it make sense to talk about global warming only in terms of temperature, or should we also account somehow for the fact that the warming comes with increased temperature and the consequences are obvious in terms of precipitation changes, extreme events, cyclones, which are all fueled by moisture dynamics that goes with the warming and increased water vapor. So this requires a little bit of an introduction to the concept of equivalent potential temperature. In my course on dynamics of atmosphere and oceans, I have in chapter 4, I have the detailed derivations of the potential temperature and the equivalent potential temperature. So in situ temperature is what you measure anywhere in the atmosphere or ocean. But since pressure changes, especially in the atmosphere, logarithmically with the altitude from the surface, there is a way to take that relation between temperature and pressure. As you remember, temperature decreases from the surface to the tropopause. So if you take any parcel anywhere and bring it to a reference pressure, like the surface pressure, then the change in temperature associated with the pressure is called the potential temperature, so it takes the compressibility into account. Obviously, when you have water vapor in the parcel and you move it up or down, you can condense or evaporate the water vapor and you end up with another temperature called the equivalent potential temperature. So let's just jump into that with that very brief introduction. It makes a big difference in terms of understanding how warming changes moisture, and equivalent potential temperature captures that in terms of the translation of that temperature and humidity change into dynamics of extreme events, rainfall, heat waves, and so on and so forth. So this is our favorite Clausius-Clapeyron equation, which we had written in a simple form with E equals A times e to the beta t, where A is a constant, beta is a constant temperature, and that's the saturation vapor pressure. So we are writing that here in terms of dAs dt as LV, the latent heat of vaporization, divided by the gas constant for vapor. This is the saturation vapor pressure, so this is where you get the exponential relation, divided by T squared. So without going through the derivatives, let's just write the approximate expression for equivalent potential temperature, which obviously is a function of the in situ temperature and humidity. So LV is again the same, latent heat of vaporization, heat capacity at constant pressure, times R. R is a mixing ratio, which is basically Q over 1 minus Q, where Q is the specific humidity at that temperature or at that location. Can be anything. Only saturation vapor pressure depends on temperature. Relative humidity, specific humidity depends on other processes that determine the humidity levels, dynamics and thermodynamics. So since Q is much smaller than 1, typically R is approximately equal to Q itself. Remembering that R here, then multiply by P0 over Ps, where P0 is the pressure at any level, divided by the surface pressure, to Rd over Cp, where Rd here, let's see, did I define what Rd is? Rd is of course the gas constant for dry air. So Cp is again the same. So remembering this nonlinear expression of equivalent potential temperature that depends on in situ temperature and pressure variations, we can write that potential temperature into a part equivalent potential temperature into a part that depends on just the air temperature and a part that depends on moisture or mixing ratio. So approximately we can split it into a equivalent potential temperature that is changing with temperature, and then consequently how humidity changes and that contribution to equivalent potential temperature. So this is moisture. This in absolute term tends to be very small compared to in situ temperature, but what we are interested in global warming is how are they changing relatively when warming happens. So we know how warming is happening because of anthropogenic forcing. For example, we have warmed by about 1.2 degree centigrade or so compared to the pre-industrial levels by now, but moisture also has changed. So how does that affect the equivalent potential temperature? Equivalent potential temperature here should be remembered as being closely related to the so-called wet bulb temperature, where if you put the thermometer then you get the in situ temperature, but if you put a moist towel around the bulb of the thermometer, then what it measures is so-called wet bulb temperature. So the saturation temperature at that saturation vapor temperature at that in situ temperature. I hope it's obvious. Okay, you can look that up. So it's literally wet bulb temperature. When you put a wet towel around the thermometer, what temperature shows up. Okay, so it's the temperature at which the moisture in the air would condense. Okay, that's easier way to think about it. So here R, this is different than this R, sorry about that, is still related to humidity. So it's a ratio of gas, epsilon is the ratio of gas constants for dry air and water vapor, so RD and RV. R is the relative humidity here, so be careful. ES0 is vapor pressure at reference temperature T0, so that's 273.15 Kelvin, and RV is a gas constant for water vapor, and hence theta AM can be written with this R, the expression being epsilon R ES0 divided by P, the in situ pressure versus the reference pressure, and E to the LV over RV times 1 over T0 minus 1 over T. This is the reference temperature. This is the in situ temperature. So you can think of it also in terms of a pre-industrial temperature and global warming. Obviously, as warming happens, this term decreases. So then R increases because this is an exponential term, right? So the expression is still related to humidity. So theta AM, EM, the contribution to equivalent potential temperature from moisture, then becomes LV times epsilon times RE as ES0 divided by CP times P, E to the LV over RV times 1 over T0 minus 1 over T times P0 over PS to the RD over CP, basically showing that the response of theta AM, EM in absolute terms may be smaller than theta ET, contribution from just in situ warming, but with warming its contribution grows faster, okay, because of this exponential term, and that's important, as we will see. And the wet bulb global temperature is approximately defined as this empirical relation 0.567 times T plus 0.393 times E, the specific humidity, saturation humidity, plus 3.94, a constant. Okay, so you can see the impact here immediately. Theta E T in the future is going to look like this with the polar amplification kind of pattern. So this is temperature, theta E contribution from temperature change, and this is the moisture component of the equivalent potential temperature. So the surface equivalent potential temperature difference between 2080 to 2099 in the future for the business as usual scenario, RCP 8.5, where the concentrations of CO2 will reach, I think, above 1000 ppm, and the radiative perturbation forcing at the top of the atmosphere will be 8.5 watts per meter squared. This is based on the average of 20 CMIP5 models, so the last assessment AR5 released in 2014. The result will not change if we look at CMIP6, which is just being released. Okay, so this difference is between 2080 to 2099 and 1980 to 1999. So the last few decades to the last 2 decades to the 2 decades at the end of the 21st century. So again, the main message is that the contribution from moisture dynamics in response to warming is going to be dramatic in the low latitudes. In fact, already many papers have been written arguing that we don't only have to worry about warming that happens in the future, especially in terms of heat waves, but we have to worry about wet bulb temperature, because at high wet bulb temperatures like 35 degrees centigrade, the ability of the human body to deal with heat begins to disappear when the wet bulb temperature is approached, because the ability to sweat and cool the body down is lost. So number of deaths can go up significantly when wet bulb temperature reaches a certain threshold. So we should be careful about just focusing on in situ temperatures and how heat waves are going to change in the future, and so on. Okay. The other result that comes out of this approach is obvious here. We're looking at the seasonal cycle, the black lines in each case, of precipitation, surface air temperature, and surface equivalent potential temperature over the northern tropical land, averaged over 0 to 25 north, and their trends for each month of the year. So here is climatology, and here is trend in millimeter per day for 40 years for rain, Kelvin per 40 years for surface air temperature, and Kelvin per 40 year for surface equivalent potential temperature. And you can see that the northern hemisphere land gets more rain during the boreal summer season, as can be expected, with the climatology already indicating that the climatology tends to be ramping up during the boreal spring months, when the ITCZ begins to follow the sun, peaks in June, July, August, dominated by the Asian monsoons, and then drops off. But the trends show that it's going to decrease in the early part of the year, so first half of the year, increase in the second half, but already dropping off in December. But when you look at surface air temperature, climatology is obviously clear. Spring and summer months are warm, winters are cooler. But if you look at the trends, there is a cooling in the boreal summer months, which is approximately consistent with increased temperature, increased precipitation, and the downdrafts affecting the temperatures in terms of trends, although it starts earlier than the rainfall ramp up. But when you look at equivalent surface potential temperature, you can see a dramatically different trend, where the equivalent potential temperature at the surface increases from July onwards into November, and in fact it peaks in October. So in terms of heat waves and impacts on health and extreme events, etc., this then becomes critical rather than the surface air temperature. Okay, so I will stop here and then come back to look at other consequences of looking at quantities that we have looked at for global warming, but now looking at looking at them in terms of equivalent surface equivalent potential temperature. I hope the idea is clear that by accounting for the increase in water vapor and latent heat acquired by the atmosphere with the warming, we end up getting more insights into how the future is going to look like in terms of quantities that are important, like total precipitation, extreme events, wet bulb temperatures for health, and so on. Okay, of course, that can be translated also into ocean's role in precipitation changes, extreme event changes, cyclones, and so on and so forth.